Section 16.5 deals with some biologically important disaccharides, and disaccharides are exactly what they sound like. So since we have the prefix di, it means that there's two sugars attached together to make a disaccharide. So we take two monosaccharides, we put them together, and we make a disaccharide. So it says here that the anomeric hydroxyl, you remember the anomeric hydroxyl, that's going to be the hydroxyl on carbon 1 of our sugar. So this is a anomeric carbon, and this one over here is also an anomeric carbon in these two glucose molecules. So the anomeric hydroxyl can react with another hydroxyl on an alcohol or sugar, forming what's called a glycosidic bond, and then water is lost to form an acetal. So if you take a look at what's going on here, is that we're making this disaccharide called beta maltose. So maltose is a disaccharide you have to be aware of. You have to know that it's made from two molecules of glucose. So here they're showing alpha D-glucose, and we know that it's alpha because the hydroxyl on the anomeric carbon is pointing down. So this is alpha. And then we have beta D-glucose over here, and we know that this one is beta because the hydroxyl is pointing up. So what happens is, when we form this glycosidic bond, we're having a reaction between the hydroxyl at carbon 1 here, and we're also doing a reaction between the hydroxyl on carbon 1 and the hydroxyl on carbon 4. And the reason they've circled, the two hydrogens and the oxygen in this pink, oval here is to show that we're losing water as a product. So we do the reaction between that anomeric hydroxyl and the hydroxyl on carbon 4 of the other glucose molecule, and we form what's called a glycosidic bond. And you'll notice that a glycosidic bond is just a type of acetal. Okay, it's an acetal between two sugar molecules. So you can see that we go from carbon, oxygen, carbon, oxygen, carbon. So if you remember when we looked at acetals, so this is how we characterize an acetal. So it's kind of like two ethers coming off of the same carbon. But this, when we have this bond between two sugars, we call this a glycosidic bond or a glycosidic linkage. And you notice that here they've called it an alpha 1,4 glycosidic linkage. So alpha means that the bond coming off of the anomeric carbon, and remember, this is an anomeric carbon. Carbon 4 is not an anomeric carbon. So this bond here is coming down. So this bond here is coming down. So since it's pointing down, it's alpha. And then 1,4, so for 1,4, because the bond, or the oxygen, is in between carbon 1 of the first sugar molecule and carbon 4 of the second sugar molecule. So, and that's how we form beta maltose. So something I want to point out to you is that maltose is always going to be characterized by having this. So maltose will always have this alpha 1,4 glycosidic linkage. Now in this specific example, they've shown beta maltose. Now the beta means that the hydroxyl on this anomeric carbon is pointing up like that. So could I have alpha maltose? The answer is yes. If the hydroxyl on this carbon, if it was pointing down, then it would be alpha maltose. So there we go. So there's our maltose molecule. There's our glycosidic linkage. So what do you have to know from this slide? That I take two molecules of glucose, I combine them to make maltose. The linkage in maltose is an alpha 1,4 glycosidic bond. And there we go. So let's take a look at what else. So it says the glycosidic linkage, a little more information on that glycosidic linkage. So that glycosidic linkage, which again is an acetal, joining the two rings can be alpha or it can be beta. Now if you go back to this slide, the glycosidic linkage shown in maltose is alpha, but it can be beta as well. So again, if the bond is pointing down like this, and this is pointing down, and it's shown on a bit of an angle, and that's just to make it easier to see, then it's alpha. If the bond was pointing up, however, then it would be a beta glycosidic linkage. So again, since it's pointing down here, this makes it an alpha 1,4. And this whole convention of putting an arrow between the numbers, this is just a convention that we use when we're describing glycosidic bonds. So a little bit more information about maltose, which sometimes we call malt sugar. So malt sugar is formed, again, by linking two D-glucose molecules together to give a 1,4 glycosidic linkage. Again, the 1 and the 4, where does that come from? It comes from carbon number 1 and carbon number 4. And there's a glycosidic bond. And remember that maltose is characterized by an alpha 1,4 glycosidic linkage. And the reason it's alpha is because this bond is pointing down. So again, malt sugar is formed as an intermediate in starch hydrolysis. And later on, we'll look at the structure of starch, and we'll see that when starch is broken down in order to harvest the energy that's found in starch, maltose is going to be one of those intermediates that we form when we break that starch down. Also, it's important that you understand what a reducing sugar is, and any sugar that has a hemiacetal group is going to be considered a reducing sugar. So where's the hemiacetal in this molecule? Well, if you look over on this side of the disaccharide, you can see here around this anomeric carbon we have carbon, oxygen, carbon, and then we have an oxygen and a hydrogen. So this part right here is a hemiacetal. And you might remember that when we have a hemiacetal, we have a reducing sugar. So it can reduce copper 2 plus to copper 1 plus, if you remember the Benedict's reagent. So that's what makes this a reducing sugar. So maltose is a reducing sugar, and you should be fully aware of that. You don't have to have the structure of maltose memorized off by heart, but you should know that it's formed from 2 glucose molecules. It's linked by an alpha 1,4 glycosidic bond, and it is a reducing sugar. A little bit about lactose. So lactose is a sugar that comes up in everyday parlance. You've all probably heard of lactose intolerance before, and if you're wondering where lactose comes from, it's a disaccharide that's formed by joining galactose and glucose. But this time, the linkage, or the glycosidic bond between the 2 sugar molecules, is going to be a beta 1,4. So we're going to have a beta 1,4 glycoside. So let's take a look down here. So we have beta D-galactose, and then we have beta D-glucose. The only difference between D-galactose and D-glucose is at carbon 4. If you notice the hydroxyl on the carbon 4 of beta D-glucose is pointing down, whereas on beta D-galactose it's pointing up here. So that's the only difference between glucose and galactose. Anyhow, so when we're putting the galactose and glucose together to make lactose, so it's categorized again, or characterized by that beta 1,4 glycosidic bond. So here's my anomeric carbon, carbon number 1 on my galactose. Here's my hydroxyl, and it's going to lose water in a reaction with carbon number 4 of my glucose. And again, in this, sort of pink oval here, they circled these atoms which make up water because we're losing water when we form that glycosidic bond. But why is this beta 1,4? Because the glycosidic bond coming off the anomeric carbon is going up like this. So that's what makes this a beta 1,4 linkage. So lactose can be used as an energy source, but in order to break down lactose, it has to be hydrolyzed into glucose and galactose. And lactose intolerance, where that comes from, is lacking the enzyme lactase, okay, which helps to hydrolyze the glycosidic bond. So the first thing you have to do is actually break the glycosidic bond. So lactase is an enzyme, which is just a biological catalyst. Anyhow, so what happens is, if you don't have a lactase, what happens is that lactose doesn't get broken down normally, and it ends up in the intestine, where it gets broken down to things like carbon dioxide, which is a gas, of course, which causes discomfort, and that's why lactose intolerance is not a good thing to have. All right, a little bit more information about lactose intolerance and something else that's called galactosemia. So it says here galactosemia is covered in these 3 bullet points. And what it says is that in order for lactose to be used as an energy source, first galactose has to be converted into a phosphorylated glucose molecule. So all that means is that in order for us to harvest the energy from galactose, if we want the energy from the bonds in galactose, before we can just break down galactose, we have to add a phosphorus atom, and we're not going to look at the structure of the phosphorylated glucose, but what you have to know is that you have to add a phosphorus to glucose, and what that does is it helps functionalize it so that it can be broken down by the human body. But what happens is, in order to get from that galactose to that phosphorylated glucose, you need a specific enzyme in order to be able to do that. And it says that when the enzymes necessary for this conversion are not present in the body, you get a genetic disease called galactosemia, which is a very serious disease. It can lead to all kinds of different problems, and even it can lead to death. Now, a little bit more about lactose intolerance. So people who lack the enzyme lactase, which is around 20% of the population, are unable to digest lactose and have that condition known as lactose intolerance. So if it's around 20% of the population, I'm sure that just about everybody who's watching this video is probably, aware of somebody who is lactose intolerant. So a little bit of information about sucrose. So sucrose is a disaccharide that's formed by linking alpha-D-glucose with beta-D-fructose to give a 1,2 glycosidic linkage. And we're going to look at the structure of that in an upcoming slide. What's interesting when you compare something like lactose or maltose, which are reducing sugars, sucrose is actually a non-reducing sugar. So what that means is that it gives a negative reaction in the Benedict's test. And the reason why is because there is no hemiacetal in sucrose. So it says here the glycosidic oxygen is part of an acetal. So you could even write here no hemiacetal. A little bit more about sucrose. It's an important plant carbohydrate. Of course, it's found in sugar cane. It's water soluble. You're probably all aware of that. If you stir, if you've ever made Kool-Aid or put sugar in coffee, it dissolves very well. So it's easily transported throughout the plant circulatory system. And interestingly enough, it cannot be synthesized by animals. Sucrose has a whole host of names like table sugar, beet sugar, sugar cane or cane sugar. And, obviously we use it as a sweetener in our food, and so much so that the average American consumes around 100 pounds of sucrose each year. And people generally regard it as an empty, just source of empty calories, But really the only deleterious effect that we know of that's directly related to sucrose is the formation of cavities. So it's directly related to your dental health. Anyhow, so let's take a look at the structure of sucrose. So here I have my alpha glucose. You remember that sucrose is made from glucose and fructose. So fructose is a sugar that has a 5-membered ring. And if you take a look at the linkage, it's a little bit interesting here. So you can see that the alpha glucose, the reason we call it alpha glucose, because the hydroxyl on carbon 1 is pointing down. So this is alpha. And the reason we call this beta fructose is because on carbon number 2, so we consider this the anomeric carbon, that the hydroxyl is pointing up. So this is beta. So the linkage nomenclature in sucrose is a little bit different than what we saw in lactose and maltose, where it's an alpha 1 beta 2 linkage. So you don't have to have the type of linkage for sucrose memorized, but you should know that it's made from glucose and fructose and that it's a non-reducing sugar. So non-reducing. Okay, and if you're wondering why it's non-reducing, well, I mentioned that before, and that there is no hemiacetal. So no hemiacetal present in sucrose. So if you take a look at that glycosidic oxygen, if you remember in the slides, it said that the glycosidic oxygen was part of an acetal. So if you take a look here, we have carbon, oxygen, carbon, oxygen, carbon. And there we go. There's our acetal. We could even circle that to make that even more clear. So that is not a hemiacetal. It is an acetal. And therefore, that is why sucrose is a non-reducing sugar. So it won't reduce copper 2 to copper 1, the Benedict's reagent.